In this chapter, we're going to explore a problem that pretty much every software development team runs into. How do you make big, complex changes to an application while making sure it's always in a working, releasable state? We're going to look at the crucial strategies teams use to move fast while still keeping their software ready to ship at a moment's notice. It's really the art of building an always releasable app. So, to make this a little more concrete, let's imagine a scenario. Your team has been tasked with completely rewriting the user interface for an application that's already live. Now, this is a massive undertaking, but here's the catch. You still have to ship new versions with updates and bug fixes every single day. So, how on earth do you pull that off? How do you make such a huge change without ever breaking the product for your users? Well, that's the puzzle we're going to solve today. All right, here's our roadmap for this discussion. We'll start by talking about the always releasable goal itself. Then we'll dive into some specific strategies for what's called mainline development. From there, we'll look at the bigger picture of architecting with components, tackle the tricky problem of managing dependencies, and then we'll wrap it all up with a summary of the key takeaways. So this brings us to what you could call the releasability paradox. On one hand, you want your application to be stable and ready to release at any given moment. But on the other hand, real-world development means making big, sometimes messy changes that can, temporarily break things. These two goals feel like they're in direct conflict with each other. So how do we actually reconcile them? Well, the traditional approach to this problem was something called feature branching. You'd make a copy of the code, go work on it in isolation for weeks, maybe even months, and then you'd have to face the dreaded big merge back into the main codebase, or what we call mainline. And trust me, that merge can be a total nightmare of conflicts and bugs. The whole idea behind continuous delivery is to flip this on its head. The goal is for everyone to work directly on mainline, all the time, keeping it perpetually stable and ready to go.
Okay, so if we're all working on the same single code base, the main line, how do we keep from constantly tripping over each other and breaking the application? Let's get into the specific strategies that actually make this possible. At the heart of it all is one core principle, and it requires a lot of discipline. Everyone on the team integrates their code into mainline frequently. We're talking at least once a day. This stops those long-lived feature branches from ever forming, where code can drift apart and create huge integration headaches later. This practice is known as continuous integration, and it's really the foundation for building a stable, releasable app. Now, this quote here is fantastic because it's so counterintuitive, isn't it? When you're facing a massive, really scary change, your gut instinct is to wall it off, to isolate it on a branch so it can't hurt anything. But the argument here is that this is exactly when you shouldn't branch. And why is that? Well, because the bigger the change, the more painful and the more error-prone that final merge is going to be. It's much better to deal with that integration pain in small, manageable little bites along the way. So how do we actually do this in practice? Well, we have a toolkit with three main strategies. First, we can hide new, unfinished features from users, even though the code is technically in the main line. Second, we get really good at breaking down big changes into a series of tiny, incremental steps that are each releasable on their own. And third, for the really massive changes, we can use a super powerful pattern called branch by abstraction. Okay, branch by abstraction is a really elegant pattern for making huge changes safely. So let's walk through it. Let's say you need to replace your entire database system. First, you create an abstraction. Think of it like a universal adapter that sits between your app and the database. Second, you change your application so that it talks to this new adapter instead of directly to the old database. This is a critical step. Third, you can now build your brand new database implementation right alongside the old one. Fourth, once the new one is ready, you just flip a switch in the abstraction layer so it starts sending requests to your new implementation. Fifth, once everything's working, you can safely remove the old one. And finally, you might even be able to remove the abstraction layer itself. This whole process lets you perform major surgery on your app while it's still running, and your users will never even know it happened. So those team-level tactics are great, but for really large and complex systems, they're not quite enough on their own. We need to start thinking bigger. We need to think about the architecture of the system. Let's pivot now and see how breaking a large application, what we often call a monolith, into smaller, independent components is absolutely essential for working at scale. So what do we really mean by a component? Think of it as a large-scale, self-contained part of your application. The key thing is that it has a well-defined API, an application programming interface. That API is like a contract that spells out exactly how other parts of the system are allowed to interact with it.
In the real world, these components often get packaged up as things like DLL files on Windows, jar files in the Java world, or SO files on systems like Linux.
So why would you want to use components? Well, for one, they help us break a huge problem down into smaller, more manageable pieces. They also allow different parts of the system to change at different speeds. Your user interface might change every week, but your core billing engine might only change once a year. And this is a huge one for big companies. Components let multiple teams work in parallel on different parts of the system without constantly getting in each other's way.
Probably the best analogy here is building with Legos versus carving a sculpture from a single giant block of stone. A monolithic system is like that stone block. Everything is tightly connected. A tiny change in one spot can send a crack running through the whole thing. A component-based system, on the other hand, is like a box of Legos. Each piece has a standard way to connect, but you can easily swap out a red brick for a blue one without having to redesign the entire structure. It's flexible, it's modular, and it's just so much easier to manage.
But all that flexibility comes with a new challenge. Once you have dozens or even hundreds of these Lego bricks, you create a new problem. How do you manage the incredibly complex web of connections or dependencies between them all? This is where things can get really, really tricky.
This leads to a classic problem that developers have a very fitting name for: dependency hell. This is what happens when, for example, your application needs version 1.0 of a specific component to work properly, but when it's deployed, it finds version 2.0 instead, and version 2.0 has changed in a way that breaks your code. The result? Your application just crashes. Trying to manage all these versions across all these different components is a massive challenge.
So if you look at this slide, you can see a simple dependency graph. That framework component on the left is what we call an upstream dependency. All the other components depend on it. This means that a single change to that one upstream component can cause a massive ripple effect, potentially forcing you to rebuild and retest every single one of the downstream components.
So what's the solution? Well, it's automation. Specifically, a pipeline of pipelines. The idea is that each and every component gets its own automated build and test pipeline. Then, whenever an upstream component, like our framework, is successfully built, it automatically triggers the pipelines of all its downstream dependencies. This sets off a chain reaction that automatically propagates through the entire system.
And the result of this is incredibly powerful. You get immediate, automated feedback. If a developer makes a change to that core framework and it accidentally breaks the pricing engine component, they'll know about it in minutes, not days or weeks later. The pipeline pinpoints exactly where that integration failed, which makes it so much faster to diagnose and fix the problem.
Okay, we have covered a lot of ground, from individual team tactics all the way up to high-level system architecture. So let's bring it all together and quickly summarize the key principles for building software that's always releasable, especially at a large scale. So if you only remember a few things, make it these 4. First, always prefer developing on the main line over using long-lived feature branches. Second, use powerful patterns like branch by abstraction to make large-scale changes much less risky. Third, as your system and your team start to grow, break down your monolith into smaller, loosely coupled components. And finally, you have to tame the complexity that comes with that by managing all your component dependencies with a fully automated pipeline of pipelines. And that brings us to a final thought to leave you with. This idea of a pipeline of pipelines isn't just a technical detail. It's really a fundamental shift in how we think about collaboration and feedback on large software projects. So the question I want to leave you with is this: how could this approach, this idea of automated, chained pipelines, change the way you manage complexity and risk on your next team project? Thank you for joining me.